Good evening. This is Anirban, and today I'm going to talk about segmentation using the UNet model. I did a short session on segmentation using the mask RCNN architecture with the Meta AI Detectron 2 framework. Today, I thought of showing a similar exercise with the UNet model. The unit architecture, as we know, and we can see here, has a set of encoder layers and a set of decoder layers, and there are connections between these. So basically, we want to use a approach which uses almost no code. Can be quickly the model can be quickly tried on a data set, and results can be shown to the industry. UNet model, as we can see here from this blog post, is very much used in biomedical applications. For example, here we can see that it's used in finding out certain problems in the lung ultrasound scans, where person may have some nodules or some problems in the lung ultrasound scans. So it is very much used in biomedical image segmentation, and it's very accurate, and that's the reason. And we feel that a similar approach can be taken for manufacturing defect detection also, by looking at the defects for various use cases. What we see is defects in the manufacturing industry are often very difficult to detect. They could be small spots on a plastic molded part. They could be, like, they are called OLG defects. There are various names to these. There could be some marks on injection molded components called silver marks, some faint marks. It's not very highly visible to the naked eye as well, but manufacturing companies may want us to find those out. And what we have seen is they have to do a human inspection over there, although there are many sophisticated instruments which do measurement and inspection. We know that, starting from the coordinate measuring machines, sophisticated inspection machines, but those are basically surface roughness machines, but those are definitely used on some samples. But most of the manufacturers that we have met has told us that they do a 100% thorough inspection, and that requires a lot of time and effort to check the components for this kind of defects. And that is where computer vision can play an important role by identifying these defects. So the other important aspect about defect detection using UNet, what I've seen from most of the tutorials which are there already, is that most of these tutorials, they're very good. They're very good. They explain the concepts very well, but at the end of it, I find that they are downloading a data set from somewhere. It could be from TensorFlow data sets, it could be some other competition repository. So it's a well prepared data set where the images are there, the binary mask images are there, and we just train the model. And not only that, we also see in most of the tutorials there is a huge amount of data, like there are 1500 images, train images, there are 200 test images, somewhere in some cases we see thousands of images. But normally what we have seen is in industry that is not the case, because in most cases scenarios we find that two things. One is the number of images we get may be very few, so maybe in the order of tens or 20s or 30s. And in such scenarios, it's very critical that we use a concept called transfer learning, which means a pre trained model, a pre trained network. Whichever model architecture we use, doesn't matter whether it's a unit or whatever it is, we need to definitely use a pre trained model which has already learned to distinguish various classes and is trained on a generic data set, and we fine tune that for our purpose. That works the best when we have few images, at our disposal. Of course, there are other techniques like image augmentation and other things, but still, the original images, if they are very few in number, training a unit model from scratch will not make sense, right? It will require a lot of images. And as we can see here in this example, this particular blog post which I opened first because it shows this architecture, the encoder layers are shaded in blue and the decoder layers are shaded in white. And there's a reason to that, because it says that these blue ones are from VGG16, which means these layers are coming from VGG16 and I can load them up with the pre-trained image net weights. And I might want to train the decoder layers only, right? That's one way the transfer learning is done in case of a unit. There are various ways. Someone may say, I will train the whole network. That's also fine. Someone may say, I will only train these last few networks. That's also fine. But mostly this approach is taken in many places. So today I will show this by preparing a sample data set. So another shortcoming, or I would say not shortcoming, I would say another aspect that I have seen missing in many tutorials is, as I said, those tutorials are very good, but they just download the data from some data sets and they say, okay, this is the data, and they just feed it to the model. But in industry, when we are going to solve a problem, it never happens like that, isn't it? Nobody from the industry and comes and says, okay, I have a repository where I have prepared the label data, you please go and use it. They don't. Nobody gives that. At best they can give us 10 or 20 images showing the defects, right? And we have to go and prepare that data. So one of the best ways to do this is using the platform called Loopr AI, which I represent. And I would like to show a quick round of annotation, image annotation for segmentation using the Loopr AI platform. And using that annotation, those annotated images in the training of the unit model. So in the process, I will also show how we can convert between the various forms of annotations. And I've seen that's one of the challenges as well when using different architectures of neural networks. I've seen some architectures accept certain formats of annotation files very well. For example, the Detectron 2, I remember it accepts the Coco format JSON and also something called a VR JSON very well readily. It uses its own internal format, which is a Python dict, but it can accept those two formats very readily. There are other networks like the TensorFlow unit model framework model architecture, which generally takes, we have seen the binary mask images, right? We have to prepare that. There are other frameworks which takes Pascal VOC XMLs. So how do we convert from one format to another? I've seen people scrambling to find out how they can do the annotation which is required for that particular model architecture. That's another thing that we address over here in the Loopr AI platform. So having said that, I will go here to the Loopr platform and try to create a data set. I'll just annotate few images to reduce the time and not go through all the images. I have about 40 or 50 images. I'll use a public data set, which is what I have to use because I cannot use a data set which is used by a company. So what I do is I create a new data set in the Looper platform. I name it. Let's say this data set is used for segmentation of cracks appearing on concrete. So let's say this concrete crack data set depict cracks. So I create this data set, and once done, I can simply drop my image files here. So let's say I take 5 such image files, drop this. So my data set is now created. Once I have created the data set, I basically need to create a segmentation project here. So I'll say a new project, custom model. So we'll say, I'll not fill the description right now. We'll say a segmentation model. The label of the defect, in this case, we know it's a crack in the concrete. We can use different types of segmentation boundaries. In this case, I'll go for freeform boundary because that's what suits me best. I can change the color if I want to. And then I have to attach my data set to this project. I can take one of the existing data sets, which I just now created. This is the one I created, 6 rows, 6 images. I add that and I submit this. So the data set is new now created. I can use any training Docker image. I can use any image. Right now I'll go ahead and use this because right now I'm not going to do the training on the platform. I'm just going to do the annotation and export that annotation in a Coco JSON format file. So once I've created this project, I can basically start my annotation, can enable the reviews. Once I say start annotation, I should be able to see the image here and I should be able to annotate the crack appearing on the concrete, which is a complex contour. There's a lag happening and could be some issue with my browser as well. Just wait a while. Okay, it has appeared. So this is my image. I can minimize it, maximize it. In this case, I am zooming out to see the crack properly. And now using this freeform tool, I can annotate this crack as accurately as possible. So this is one, this is one. So I submit it. The next one appears. Submit this. And this way we can do for all the images that are there in this set. So I'm doing for a reduced set of 5 images to reduce the time taken. This is a pure annotation work where the person who is doing the annotation needs to know where the defects are located. He will need a domain expertise in most cases. Here it's a crack in a concrete which is something we see almost on a daily basis, so I can easily annotate it and get done with it. But in most cases, what we have seen in manufacturing defects, to the untrained eye, the defect may not be visible also. So we might require the help of people who are working on the shop floor to do these annotations. Or it could be that they train the people who are doing the annotations so that they can do the annotations accurately. And it goes without saying that the machine learning model can only do as good as the input which is given to it. So if the annotations are not annotated correctly, obviously we cannot expect the deep learning model to do any miracle. So here we are annotating this with a, and here also I'd also like to add the freeform tool helps in these cases a lot, because here, mind you, we are doing a segmentation, not object detection. So we want to delineate the actual crack which is appearing on the concrete. I'm using this data set. I'll give the details of this data set when I do the training, but because it's a public data set which we can use. My last image for now is a thin crack. I'll label this also, annotate this also, so that the model can train and try to detect the hairline cracks as well. So I am done with the annotations. Now what I do here is I go to the exports tab and I say I want to export these annotations, create a new export, and I say I want a Coco JSON, and I say since we have the facility to get these annotations reviewed by an expert, and the expert can review as negative, send it back to the annotator, all that is also there. Right now we are not using that, so I'm saying take all images, proceed, confirm and export. So it's export in progress. Once the export is done, we should be able to download it. Export is done. So we have a download button. We click it here and we should see this particular JSON downloaded. It has got downloaded and we can open and check it up as well. So this is the JSON. I'll just put it on a JSON viewer right now. So we can see that it is following the COCO structure with the images node. There are 6 images, the annotations node, and each annotation is pointing to one image. The categories are there. The category should be basically a category called crack. That's what we are trying to detect here, right? So this is a proper COCO JSON. That's what we can check here. And now this COCO JSON is what we can use in our training process, which I'm going to do now using the collab. So I come here. I just what I am trying to do is I'm trying to use this COCO JSON to train a TensorFlow unit model. So the first step for that is I'll upload the images and the JSON. And what I need to do is I need to create binary mask images which can be input to this. So for that, I will create folder here. I'll call it defect data, and in this defect data I can upload this JSON file which I downloaded. So this is the JSON, which is done in a similar manner, only that it has more images, which is already prepared. It has about 40 to 50 images. So I'm uploading that JSON file. And then what I need to do is I need to create two folders for images and masks. Created this. In this images folder, I'm going to upload the images from the whatever data set I have created in the platform, which I have kept somewhere here. Right. So I go and upload these concrete crack images. So this is basically a data set which is having concrete cracks from a public data set, and I'll give the URL soon. So it's like this. So basically we are trying to see if we can train a model which will segment these cracks very well for us. And this is very much similar to a manufacturing defect. So we can definitely try this approach. Now the framework that I found very good to use and very easy to use with a minimum amount of coding is one of the frameworks called segmentation models, and this is the link to that. I've given the link in the collab notebook. Anybody can check this. This is the link to that, and basically it's called segmentation models. uh, it is a Python library with neural networks for image segmentation based on Keras and TensorFlow. The reason we like this library in industry is these features. It has number of model architectures including unit. Today I'm going to show unit. It has other architectures as well. The important thing is I can change the backbones for each architecture. So I can use a BGG16 backbone, I can use a ResNet backbone, I can use a efficient net backbone, all with just one line of coding, right? And all these backbones have pre-trained weights for faster and better convergence. This is most important, as I was saying, because in industry, what we have seen is in many cases the number of images that we get may not be huge number. It may not be in hundreds or thousands. It may be in tens or twenties at most. We have also seen customers who might share one or two images and ask us to train a model on that, right? So it is wrong to say that a customer will come and give us 500 images or 1000 images and then only we'll be able to do. No, we can't say that. So that is another thing aspect I have seen in most good tutorials also, that they assume that that is the case. They download from TensorFlow dataset or some other Kaggle dataset where there are 1500 images. Somebody has nicely prepared and kept it. And now you try all your things and see what is the best accuracy. That's fine. But I have not seen, at least in industry, anybody coming up with that kind of a data set. So it's very important to leverage pre-trained weights. That is the concept of transfer learning. That is what can be done again with one line of code. And it's not even a one line. Within a line, we can just say that please use the pre-trained weights. It has different types of segmentation losses, which we can compare and check which one is giving us better accuracy, right? So these are some of the advantages, and having said that, I'll go ahead and start with my experiment. So here is my collab notebook where some of the requirements. TensorFlow, this version we have seen works best. Segmentation model is a library, Python library, which we'll be using for a low code approach to unit segmentation. And of course, we need Albumentations, which is a very fast PyTorch based library, which can be used to in TensorFlow as well, which can be used to augment the images, right? So let's get started. I'll start up this and install this. I should have probably kept all these things installed. But let's see. Hopefully, it will not take much time. It looks like it remembers something from my previous session or not. I don't know. It's actually Google Colab by default comes with TensorFlow 2.12, and I found there's a issue compatibility issue with TensorFlow 2.12 with this particular library. So it's better to use 2.10, which is also quite advanced. So there is no issue in that. It's saying it's uninstall the TensorFlow 2.12, and then okay, it has installed the Python library that we were looking for. Some of the dependencies which it's already finding. Okay, so it's better idea to restart the runtime after changing the version of TensorFlow. So let's do that. And let's see the version of TensorFlow. It should show up 2.10.0. Yes, indeed. So we do our basic imports from TensorFlow, import Keras, image data format. This is a library which we are using, import segmentation models as SM. Right. This is an important library which is used to convert COCO format JSON to binary mask images. Because as I said, TensorFlow unit segmentation accepts binary mask images. So now we have COCO JSON. In most platforms, COCO JSON is standardized. So how we can convert that? That is where we'll use this PyCoco tools library. Albumentations we are using for data augmentation. OpenCV, we might need to visualize the images, write the images, read the images, and matplotlib. So loading the data set. So when we want to load the data set, basically we will use this concrete crack data set, which is annotated on Loopr AI platform. The Loopr AI platform produces COCO JSON, and this will be converted to a set of train images plus segmentation masks, as I was saying. So there is a train set, there is a validation set, there is a test set. Now we haven't created the masks, mind you. We only have the images. The mask folder is empty because I have a Coco JSON which has the information about these uh, defects, which we just annotated and produced these JSONs. But and we have the images, but we don't have the segmentation masks. So that is something we need to produce. So we'll create these directories. Defect data. I need to create some more directories. So we can create this in code as well as in hand, doesn't matter. Train, which will have the train images. So train and val we definitely need for now. Well, it'll have the validation images, and val annote. It will have the validation segmentation mask. And similar way, we can define the test and test annote. So once we have done this, we basically initialize these variables: x train directory, y train directory, the train and the train annotations, valid x validation directory, y validation directory, x text test directory, and y test directory. Okay, we have some utility functions, data loader and utility functions. Important here is how we read the images, create a class data set, how we read the images and apply the augmentation and pre-processing transformations, right? So that is important. Self dot augmentation, and it is also doing self dot pre-processing. These functions are defined. Data loader, right? And this is very important. The coco 2 mask. The coco 2 mask is something which we'll be using initially to convert the image into binary mask images by using the information from the coco json. So here is my image directory, which is defect data images, where I uploaded all my training images. Here is my mask directory, which is now empty. Defect data mask, there is nothing inside it. There is inside the images, I have the images, which is the cracked concrete images. I'll just pull up one image to visualize it. So these are the images over here. The mask directory is empty because I don't have any mask, but I do have a JSON, which is this particular JSON. I make sure that that's the file I have. I will say file not found or something like that. Yes, okay. Now I run this coco to mask function. So what this does is it basically loads the coco format JSON into a coco object, and in this coco object it iterates through the coco.images. So for each image in that JSON, there is a image object coco.images image ID, and from that image we can open that file. We can get the category IDs, that is the classes of defects, the annotation IDs, right? The annotations which are the defect annotations of the defects, and we can say annotations equal to coco.load ans annotation IDs, and this is where the transformation comes. Mask equal to coco.and to mask. It provides this function and to mask, right? So for each of the annotations there, we just keep on adding these masks. Coco dot and to mask ans I, right? And then we say that we apply this filter that anything which is greater than 0 is actually white 255, rest is all background, and we just write this image in the masks folder in the mask directory, right? So let's see, let's apply this. It's working. So it's done. So once it's done, we can go inside the mask folder and check. So basically the important thing here is there should be a mask image created with the same exact same name as the image name. That's how this will work. So this is 0349695A something dot jpeg, and this is also exactly the same. And if we look at this image, let's see how this looks. So this is the binary segmentation where we can see the concrete crack has been annotated as a binary mask image, right? So Another check we can do quickly is we can check the number of images in the image directory versus the number of images in the mask directory. Now they should exactly match. So image directory is where I have the images, in the mask directory. Now we see that mask directory has 52 and image directory has 56. So there is a mismatch. Now this mismatch is created because I have downloaded some extra images which was not there in the Coco annotation JSON due to some reason from the platform, right? So what I'm going to do now is very simple. I'm going to iterate through the images in the image directory, and I'm going to create a mask path with the same file name. I'm going to append the mask directory, and I'm going to check for this image, is there a corresponding mask. If it's there, it's fine. If it's not there, I'm simply going to remove that image. Print okay. So that way my masks and images will match exactly. Now this is not supposed to happen. The way I have downloaded the images, it created some extra images in the images folder for which there is no annotation in the annotation JSON, right? So that's why the Coco to mask can only create binary mask images for those images which are there in the annotation JSON. So it has created this many masks, but I have more images than that. So I'm just going to remove those images. Otherwise the training will fail. So it says okay, wherever there is no mask, it has removed those. So now if I go back and run this, I should see exactly same in the image and in the mask. 52 in the image directory and 52 in the mask directory, right? Okay. So I'm good now. Now I have one more task. Now I have got my images and masks into folders, right? Now I need to distribute it as train sample, as validation sample, right, which will be used as part of the training process. That is, it will keep on checking the accuracy on the validation set, and it will keep on adjusting the weights. And finally one test sample which will be unseen data, which will finally use to evaluate the training. So I need to split these images and masks. So that is what this does. It splits the mask images. So what it takes is image directory and the annotation directory, and also an array of images, and then it says give me the train directory, the train annotation directory, the validation directory, the validation annotation directory, and the test directory and the test annotation directory. Now, as a purist, somebody may say, okay, why do you have a method with so many parameters? It's true. I mean, it's not good to have method with more than 4 parameters. But right now, I'm not really too much concerned about that. Someone can refactor this and make it a method with lesser parameters. So all this does is shuffles the images. As you can see here, it creates the training length, val length, and the testing length based on a ratio of 60%, 20%, and 20%, training being the 60%. And then it creates a random sample from the array to determine the shuffled set. And from the shuffled set, it now uses the training, validation, and testing sets. Now, this can be used as an input to cross validation also, which I don't see people using much in segmentation, though they do in other machine learning problems. But one can easily do this multiple times, let's say 5 times, and get 5 different accuracy values and say the accuracy I'm getting is actually the mean of this. But doing the shuffling is important because it sometimes happens that the train images are very well formed and the validation images are very well formed, so it might show a very high accuracy, and while doing the testing we may get very low accuracy. Shuffling is very very important in my experience, at least. So that's what this does basically. So I create an array of images by picking up the images from the image directory. That's all this image array does. So it appends the images. The image array length is 49. That's what we had in the images directory. Oh, images directory. This is image directory. Okay. 52. Okay. Let's see. Okay, there are 49. Okay, I understand what's happening. Okay, okay, okay. I've got 49 images in the image array, and let me see when I split what happens. So it has divided into 29 as test as train sample, 29 images in the masks and 29 in the annotations, 9 as validation, and 11 as test. 49. So I've got 49. So I'm not so sure why here it says 52. What's the reason for that? Little bit surprised. Okay, 50, 51, 52. It's counting these lines also. That's the reason. Okay. Okay. We can do maybe grep .jpeg uc minus l. 49. Now I get 49. The same thing I can do for the mass directory. Shows 49. Okay. So we are good here. Mhm. So this 49 has now been distributed into train, validation, and split and test. Now we look at the data and visualize maybe few images. So let's take a look at, we create this dataset object with the train samples, and we take a random position in the dataset, maybe the fifth element, and we visualize the image as well as the mask. We can call it defect mask. So this is what the defect is, and the mask created is like this. Okay. Okay. Another sample. So this is the defect. This is the mask. So it looks okay to me. Now we are going to introduce the concept of augmentation using augmentation library. So Users will know that augmentation is one of the best and effective ways of augmentation. So here we are using certain augmentations like horizontal flip, shift, scale, rotate, Gaussian noise, adaptive histogram equalization, random brightness, random gamma. And we may not use so many. These are with one off, and with probability values. I just picked it up from uh, the blog, and there it's there. I mean, blog means this particular website where this library is explained. They have tutorials, and this is taken from that. So one can play around with this and change this, and may not use so many Gaussian noise and perspective. I'm not sure, but what's important here is these two things. These are resizing the images, and these has to be same for training as well as validation. In case of validation, we don't do augmentation on the images because it might basically not show the accuracy in the correct way. So all we do is resizing, and it's important to resize the train and the validation images in the same way. So we whatever we use here, we use the exactly same thing here. So one is we use a pad if needed, which means if the image is of a lower size than 320, it will add black pads in the surrounding region, which is the correct way of doing the things. We should not blow up a smaller image into a higher dimension. I've seen that always gives worse results. I've seen this resizing has to be done very carefully. I followed this always in all my computer vision projects, and it has been reviewed by senior data scientists from customer organizations who are PhD in their field, and they have said this is the correct way. So very important that when the image is of lower size than the actual size we are trying to resize it to, we just add a black border. But if it's of a higher size, we can use a resize. Here, I am still not doing the best practice. I would like to use something called the interpolation method as a Langsource filter, and that I don't see is there. So I will quickly try to check it out from my code base. I know I have used it. Interpolation equal to 5, and always apply equal to true. This is important because I want to use the best interpolation. The Langsource filter has been seen that it gives the best results in most cases, so I will use that. And one can look up the albumentation documentation on the resize method. What are the interpolation methods available? What I saw is 5 corresponds to the Langsource filter, so I'm going to use this. So I define these methods, and the pre-processing is also important here. The pre-processing function which we send here, basically it's predefined by this segmentation library. It basically normalizes the image by dividing by the 255 and all that. So now I create a data set where I define the augmentation. Earlier, when I loaded the data set, here I didn't specify any augmentation. Same data set now I load from the same directories, but the one is the actual images, one is the mask images. But here now I specify the augmentation, saying get training augmentation, and I see some samples. So some random samples. So here I see that the image has a Gaussian noise. The image has also been reduced in scale. Because it has been reduced in scale, there is a black border added, but the cracks still appear in the correct position. That is something I can see from the mask. I can see another image here. So in this case, I can see that there is an image with some kind of noise added, and I can see that the masks in the correct place. I can run it on the same image, and because of the probability, multiple augmentations will be applied, and we can see that also. So there is some kind of blurring happening here on the same image. I keep running this. Due to the probability and one-off operations, we should see multiple different augmentations happening, which is all going to be applied at runtime to augment the images. Here's one more where it has been resized, but we can see in each case the masks are in the correct place. This is probably flipped, but still we can see the mask also was flipped. That is important to note, right? So this is our. So now my segmentation model training will start, and here I can see that there are a few parameters which I have set. Firstly, the most important is the backbone. The backbone, I can use ResNet 34, I can use efficient net B3, I can use VGG 16, I can use any of these values. The batch size, the classes, which is crack for me, learning rate, the number of epochs, and I get the sm.get pre-processing for this backbone. So based on this backbone, it will return the pre-process method which is being fed to the dataset at runtime. Right. So pre-process input is a function which I'll be using to create my datasets, and we'll see that in short while from now. So the network parameters, the activations, depending on the number of classes. If I have a multi-class segmentation, I'll use softmax. Right now I have one class, so it will be a sigmoid. So this is the one liner which creates this unit model. I do not go through this entire step of creating this unit model step by step, because I want to go for a low code approach. The important aspect here is I can use this backbone the way I want to. I can keep changing the backbone layers of the unit very conveniently. It's just not even one line, it's one word in this one line. So I can use the backbone as ResNet 34, I can use the backbone as efficient net B3, I can use VGG 16. It can be one of the 25 types of backbone layers which is available in this framework. Activation is activation. Now this is important. The encoder weights equal to ImageNet, which means please load the weights from the ImageNet trained pre-trained model. I should also set the encoder freeze equal to true, because I want to train only the decoder layers to use proper weight transfer learning. I can do it without that also. In that case, it will train the entire model. So I run this. I run this. Now my optimizer, I use Adam optimizer. It's downloading the pre-trained weights. The ImageNet weights is done that. I use the Adam optimizer. I am using a loss which is a combination of dice loss and focal loss. Now this is again, as it said here, it can be a simpler loss than that. In this case, this is showing how different losses can be used in this framework very easily. The metrics, again, it can be IOU score, it can be F1 score, and I compile the model with the optimizer, the loss, and the metrics. Here is something, a tidbit, sometimes we find that while working on collab notebooks, it creates these uh, extra directories, and which gives error during the training, and I spent many hours on one day to fix this, and then I found this is the cause. Instead of images, it's finding something called IPU and NB checkpoints, right? So it can happen. So I was just running this to make sure it's not there. I'll be more careful. I'll run it for the train folder also. In case it is there, it will remove that. So it's not there. Hopefully it's not there in the train annotation folder also. So now I create my train dataset using the dataset function which is defined for us above, which takes the train images, the annotation images, the binary segmentation masks. Here I define my augmentation function, which I'm going to use, and the pre-processing function, right? Same way I define my validation data set, but note here I am using the get validation augmentation, which is only the resize aspect of it. And the pre-processing works in the same way, right? I do the use the data loader of the PyTorch to create the data loader object, and this is what is going to be finally used in the model training process as a train data loader. It's important here. We faced a number of errors here, and we had to fix it. That the train data loader and the validation data loader should be exactly of the same size. So that's why this asserts or these print statements can also do for checking. But I remember we had to fight with this for quite some time, because we due to some reason we gave a little bit of a different size in the train and the validation. Maybe we give the correct size, but the batch size was different. Even then it will crib and it will fail during the training. Callbacks, we use the model checkpoint callback, which saves the best weights. We use the reduce aileron plateau, right? So let me run this. Let me see what happens. Yeah. Okay. And I will do up to this, and then I will train the model. This is going to take a while, so maybe I'll start the training and come back after a while and again resume. So let's make sure the training is running fine without any errors. Starts with a IU score of 0.56, which is not that good, but we are hoping that over the epochs it will grow better and the loss is going to come down. So we can see already it has gone to 0.63. So the training is going fine. So now here we are. We have completed the training of 40 epochs, and we can see that the results. We can plot the IOU scores, the train and test, basically the train and validation, and should be called val. It's not test. So looks good to me, although the val loss went up little bit for the first few epochs, but then finally came down steadily. We can check the output. The output should be saved in this output folder, the best model. So we have put a check callback here, model checkpoint. So the best model is saved here, and we can check that. So we can see this a model here. The size is about 293 MB, and now we can do the model evaluation. We can load the test data set from the test directory, the test image directory, and the test segmentation mask directory. Obviously we do the validation augmentation for the test data and the normalization, image normalization. So let's see. We load the best weights from the checkpoint. Again, this is one step I keep doing. Sometimes it happens that these folders are created. I'm not sure. It's basically some temporary files created by Jupyter notebooks. So right now it's not there. So we'll say model.evaluate and we'll print the metrics which we get from the model. So we see that the mean IU score is 0.97 and the F1 score is 0.98, which is pretty good results. Having said that, we'd like to visualize some of the results on the test data sets. So what we do is we take a random set of three images from the test data set, and we do the prediction, to do a model dot predict, and the probability mask that we get, we just display that along with the ground truth mask, which is basically we have already have in the test data set. We have the test images as well as the segmented images. So let's see this. So these are the three samples we have got, and we see that the ground truth mask is like this, and probability mask looks quite good over here to me for these images. It is getting the cracks, that's for sure. So now we'd like to see, there's one more thing I've seen, that we need to overlay this image, this mask image which we are getting as a prediction on the actual image to show the defect in the actual image. We can't show something like this to a customer, right? So I'm trying to do that now. So for that I wrote a new class called test dataset where there are no masks. So this is basically to simulate the condition when we are getting some test images flowing in where there are no annotations as such. So it's a copy of the same dataset method but removing the masks. There is no mask concept here, it only returns the image. The reason I'm using a test data set, I could have loaded an image directly and just try to predict on that. The reason I'm using this data set concept here is basically because I want to use the same pre-processing function for the image which I used when training the model. The self dot pre-processing and the self dot augmentation, where I'm giving the same kind of resizing augmentation which I did for the validation dataset, and the same kind of pre-processing operation to normalize the images. So that becomes very convenient to me. I don't have to try various libraries and all that because that is already what I'm doing. The only thing is I don't consider the masks because this is an image which is flowing in from some unknown place. So there is no annotation for this as yet. So I create the test dataset from the test folder where the test images are kept. But as we can see, there is no mask directory input over here. So I create the test dataset, and then I take at random a dataset at any position, and I create the probability mask by doing a model.predict, and I visualize the mask. Okay, and I write this mask finally. This important step, though it seems very small, but I feel it's important because I write the mask as an image, right? And if you see, we can see this image. It should come in here in this folder, right? So this is my mask, which I've got as a prediction. And this mask I will now overlay on the actual image. So my image was test dataset number 5. That's my image. So I read the mask image and I combine this using cv2.add function. So I can see that the mask has been applied on the crack and it is kind of detecting the crack quite well. Few places it's not overlapping with the crack, but that's understandable. Maybe we need more training. We can experiment with different kinds of backbone layers, different training rates. Maybe the augmentation we can play around a little bit, but that's what it is. Finally, we want to overlay the binary mask on the actual image, so and see the result. That is what finally a business user will want to see. You can take one more data set, some other data set, maybe some other index number, we can say, uh, whatever it is. So we create the do the model dot predict on the image, visualize that ju- as a pure binary mask, and then once we write the mask image, we can just read the image and the actual and the mask, and overlay the mask on the image and see the results. So that is how it is. Finally, since we saw the model size was quite high, we can convert this. Since we are in TensorFlow framework, just by using 3 lines of code, we can convert this model to a TF-Lite model, and we can see that that brings down the model size drastically to 18 MB. And this model is ready to be deployed on a miniature device like a mobile or somewhere. So using TensorFlow as a framework has its own advantages. One of these is natively supports TF-Lite, and of course other quantization frameworks like the Onyx converter and all that is also there. But just wanted to show this. So that is all that I had in this session, where I wanted to show in a nutshell how we can do the unit modeling on defects using a very low code approach, and still vary the backbone layers, vary the learning rates, vary the image augmentations, and as well as the batch size and all those parameters, play around with all those, and finally see the results, how the results are coming, evaluate the results, and most importantly, how we started off by creating a Coco JSON. We didn't have to run to various tools to see which tool will give me binary mask images, maybe MATLAB, maybe Level Studio. We need to procure that, or is it a open source? Nothing like that. We use the same tool. We use a Coco JSON, but convert that conveniently to binary mask images and use that as an input to my segmentation model. So I can easily change the model backbone here. All I need to do to change the model backbone here is I need to give here, as if I want to make a very light model, I can use the efficient net B3 backbone, right? And rest of my code remains the same. There is no change in the rest of the code. My backbone layer changes from RESTnet to efficient net B3. Or I can give it here VGG16 as well. So I can do this as well. So it's downloading the VG16, and as we can see, it is basically downloading, from the GitHub of Francois Cholet, who is the originator of the Keras framework. We can see here. So it's downloading that. It works the same way. All I'm trying to say is, the entire process works the same way as we keep varying the backbones and the various other parameters, right? So that makes it a very convenient Python library to apply the unit model uh, on industrial problems. Hope it was useful for newcomers. I know experienced professionals will know most of these things, but we had to struggle a lot to see how we can apply this very accurate model architecture called UNet and still get very good results with a very few number of images without having few thousands of images, even with a few number of images, by loading a pre-trained model, and by changing the various backbone layers, checking out the model accuracy uh, with the IOU scores, using various loss functions, and how we can do it quickly. And we found this Python library to be very useful. So I thought of sharing this. Thank you.